d prime of t is, this is 0, so this is 5, but cosine is negative sine.
You're not sharing anything. I can't see.
Oh, I'm not sharing, of course. I'm selfish. Now I am.
Yes, now I see it.
So this is 0, this is negative 5 sine of 0.503 t minus 6.75 times the inner function prime, which is 0.503. Now I have to multiply. Lazy people use calculators. I have to multiply 0.503 because I'm too lazy to calculate, times 5. So 2.515. So that's all I have. Negative 2.515 sine 503 t minus 6.75. So now I have to plug this in the graphing calculator and plug in whatever they're asking us to plug in. So in y equals, I have negative 2.515 sine, oh no, negative 2.515 sine of 0.503, another parenthesis, x minus 6.75, close, close. And what are the numbers?
It says 2 a.m., 4 a.m., 7 a.m., and noon. But does that have to do with when high tide occurs?
Ah, look what I did.
Because it says the natural period of oscillation, it is a little more than 12 hours on a day in June. High tide occurs at 6:45, or does that 6:45 not matter? I thought we had to do something like, yeah, because it's it says T is hours after midnight. So I guess 6:45 doesn't matter then?
So let me say, can I read the problem again?
So the natural period of oscillation is a little more than 12 hours, and on a day in June, high tide occurs at 6:45 a.m. This helps explain the following model for the water depth d in meters as the function of the time t in hours after midnight on that day. So 6:45 doesn't relate to anything, right? It's just hours after midnight?
I think so. What does T? I don't see the problem, so I have to trust you. So what does T say?
T is hours after midnight, not hours after sunrise.
So the rate in miles per hour, or what is it? I think it's in kilometers per hour. Meters per hour.
It just says depth.
Meters per hour. Yeah, but we are looking at the rate of change. We have to have 2 measurement units for the rate of change.
Yeah, meters per hour.
So how many digits do they want?
2.
So 0.38.
But so hold on, it's not asking for that. It's asking the times are 2 a.m., 4 a.m., 7 a.m., and noon.
Oh, so that's,
which is why I think 6:45 has nothing to do with the problem.
Oh, okay. For some reason I thought it was okay. So 2,
4, 7, and then 12.
So 1.72, 2.49, 48, 2.48, negative 0.32, and negative 1.21. That's the rate of change.
So negative
1.21.
So 7 negative. Oh, I put the decimal points. All right, so I think I was being distracted by the 645, but I don't think that has anything to do with the problem. There's just extra information. Oh, what was the 4 again?
2.47.
7.
How are we doing with that?
Yep.
Good. Next question. Anybody?
I think.
Was it okay? Okay, perfect. Anything else you would like to work on?
I would like to work on some more related rates.
I'm ready.
I don't have any specific questions. I guess I could pull something up from somewhere. Let me see.
Related rates are in 3.9.
Yeah, 3.9.
I would definitely recommend go back and redo the problems we did in that class. Those are a very good indication of what to expect. And you have the videos and you have the lecture notes. It's a very good practice.
I guess we do this one where it's like water's leaking out of a tank at a rate of 8,000 cubic centimeters per minute.
Okay, so this rate has to be dV over dt, and if it's leaking, in other words, the volume decreases, meaning it's a negative rate.
And then it's the tank is water's being pumped in. Actually, it's being pumped in, but it doesn't tell you what it is. The tank has a height of 6 meters, and the diameter at the top is 4 meters.
But is it cylindrical? Is it?
Yeah, cylindrical.
Okay. So you said
it's inverted conical, actually.
So it's a cone?
Yeah.
Okay. So what is the diameter here? Or the radius here?
The diameter at the top is 4, and the tank has a height of 6.
Centimeters?
Meters.
Oh. And this is in centimeters?
Yeah, it's centimeters.
And the height?
Is 6 meters. Sorry.
So then D equals 400 centimeters, and the height is 600 centimeters. Okay.
Yeah. It says if the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, we find the rate at which the water is being pumped in. So
so which problem is this, so I can open the book?
Oh, it's 9 of 3.9.
Problem 9?
It's on the web assigned.
Oh, a web assigned. So can I just look and see?
Yeah.
So let me share the screen and get to it. So I was working with a student in Calc 2. So let's go back to Calc 1. I was here with Calc 2. And you said it's 9?
Yeah, 9. The numbers don't matter. I just want to know how it's done,
No, I can use your number. So the only difference, I guess, is just they have 6,000 in my example, and you have 8,000. That's fine. We're going to use 8,000. So what is speaking of an inverted conical? Okay, so it's a cone. Good. So it's leaking, meaning the rate of change is negative. I haven't really read the problem, but that's my thinking for now. At the same time, the water is being pumped into the tank at a constant rate. Okay, so it's leaking, but also it's pumped in. Okay, the tank has height 6 meters, which is 600 centimeters. The reason I have to change everything in centimeters because, first of all, they're asking us centimeters cubed. The volume is changing at centimeters cubed. I cannot use meters, right? Everything has to be in centimeters, or centimeters per minute, or cubic centimeters per minute. Being pumped into, okay, constant rate. The tank has height 6 and diameter at the top is 4. So in other words, the radius is 200 centimeters at the top. If the water level is rising at a rate of 20 centimeters, so the water level is dH over dt, which is 20 centimeters per minute. When the height of the when the height of the water is 200 centimeters, find the rate at which water is being pumped into the tank, the constant rate that we are talking about. Round your answer to the nearest integer. So they want integer. And they want rounding. Okay, so let's think about this problem. So it's going out at this rate, but it's coming in at a different rate. And this is a fixed rate, fine. And they're asking us, they're telling us actually that, let me just address that one more time. If the water level is rising at a rate of 20 centimeters per minute when the height, so if the level is rising, then I'm expecting an answer that overtakes the 6,000, right? So when I pump in water and it's coming out at 6,000 cubic centimeters per minute, but the water is rising. If the water level is rising at a rate of 20 centimeters per minute when the height of the water is 2 meters, then my thinking is that the rate that I pump in water into the tank must be higher than 6,000 cubic centimeters per minute. Find the rate at which the water is pumped into the tank. Okay. So the volume of water here at a particular instant, I'm going to call it V1. So V1 at any instant is the volume of water existent in the tank minus what is coming out. So let's think about this. This is very interesting. At any particular instant, the volume is in the tank is what is coming in minus what is coming out. Okay. The volume of the cone, if you remember, it's 1/3 pi r squared times the height. Easy to remember because the volume of a cylinder is area of the base times the height. You only have to do, all you have to do is put 1/3 in front. Okay. we are also given the fact that at a particular instant, when the height is 200, dH over dt is 20. So this V is that V. V1 is, remember with this, in this particular situation, we do have to use similar triangles. So this is the radius of 200 right here. This is what is, I'm going to call it R1. This is known 600. So the volume up at the particular instant, this instant, but I cannot use 200. The volume of water is, I have to determine this height. So similar triangles, this triangle is similar to this triangle. So big base over small base, 200 over R1 equals big length, so I'm going to call this H1, big length, which is 600 over H1. Okay, so I'll simplify by 100, and I'll also simplify by 2. So I have 1 over R1 equals 3 over H1. I'll flip both. So then R1 is H1 over 3. Now I can express the volume of water here. So the volume of water, V1, is 1/3 pi r squared H1 over 3 squared times H1. So V1 equals 1/3 pi squared with squared times another H1, so it's H cubed, over 3 squared, which is 9, or V1 equals 1 over 20 pi over 27 H1 cubed. Okay, I have the rate. I'm given 20 centimeters per minute when the height is 200 centimeters. Okay. So this is my V1. So dV1 over dt equals pi over 27 times 3 times H1 squared times dH1 over dt. This is 20 centimeters per minute. H is 200, so this will be 200 squared. So dV1 over dt equals pi over 9 times 200 squared times 20. I don't have to show this with the computer, so 200 times 20 divided by 9 and times pi. .68. Okay, so I have the rate of this. I have the rate of this. and I want to determine the rate of this. Okay. So I'm going to write this again. V1 equals V2 minus V. dV1 over dt equals the unknown dV2 over dt, which is unknown, minus this one of 8,000. So therefore, so dV2 over dt equals this, minus 8,000. They want the most.
Wouldn't it be plus 8,000?
I have to subtract it from.
Because in the very beginning, you had it as minus 8,000. Like you had it when it was coming out.
Yes, I have to subtract it from.
She did like a double subtraction on something that only looks.
Yes. So this. So one more time. The volume of water at any point in time is what it's coming in minus what is going out.
Yeah, and you have that as negative 8,000. That should be 8,000.
So minus what is coming out. Okay. Yes, I'm thinking of, exactly. So this is at any point in time, what is coming in when it's going out. So this minus what is going out. Okay.
Yeah, I'm just saying that.
No. You're. I wrote it initially, and then I thought of the same thing, not to make sure that. So, at any point in time, the existing volume of water is what is coming in minus the 8,000. Okay? So plus 8,000. 7, 8. And since it's 6, 8, 287, 253.